Math 2414, Trigonometric Substitutions, Video 1. What if a substitution fails? For the students in my current class, hopefully you saw the announcement about why this video is being made on Zoom instead of me being in a classroom at a whiteboard. But regardless, the show must go on. To motivate what's going to happen in what is the second half of Chapter 6, Section 2 of the textbook that we're currently using, the first half being trigonometric integrals, I'd like to compare these two integrals and see what we can make happen. The integral on the left, the integral of x times the square root of 1 minus x squared dx, is actually a pretty straightforward substitution. So let's jump right into it. Remember that the purpose of a substitution is to transform an integral to match an integral rule. That, coupled with the fact that we have a square root, which we're going to treat as a 1/2 power, means that we want to try to transform this integral to have the form the integral of u to the n u. In other words, the power rule for integrals. So let's figure out a substitution to use. And it looks like, well, the thing with the power is going to be the 1 minus x squared, so we're going to let that be our substitution. Let u equal 1 minus x squared. Then du, negative 2x, the derivative of 1 minus x squared, x squared. Let me say that again. Du equals negative 2x dx, since the derivative of 1 minus x squared is negative 2x. And as I mentioned in previous videos, I'm going to transition my approach to substitution. When I initially reviewed it, I suggested solving for dx and then substituting that expression into the integrand. But I like to focus on building the du package, meaning that every piece of the whatever du equals, we want present in the integrand. So for example, our du contains a dx. Well, guess what? Every integral will have some differential. Folks, I'm making some adjustments here. Got it again. Every integral will have some differential in it. We need an x to build the du package, which we have. And we need a negative 2, which is not currently present in the du in the integral. So being a constant factor, we can just squeeze a negative 2 in here and balance it with a negative 1/2. And that negative 2 will become part of the du. So everything double underlined will become du. And of course, the 1 minus x squared under the square root will become the u. So this integral will transform pretty quickly. We'll have a negative 1/2 in front, integral. All three double underlined parts in blue become du. And the part under the square root becomes a u, but we don't integrate radicals, we integrate powers. So instead of writing it as the square root of u, we'll write it as u to the 1/2 power. Pretty straightforward integral now. We have the negative 1/2 times, add 1 to the power to get 3/2, multiply times its reciprocal, 2/3. Don't forget the plus c. And then simplify. Well, in our fractions, we're multiplying, so we can cancel these 2's. That'll leave us a negative 1/3. And the u can go back to being a 1 minus x squared. But you know my opinion about how the answer's format should resemble the problem's format. My problem started with the radical. I'd like to end it with the radical. A 3/2 power means that we're going to take a square root, raise something to a 3rd power, and that something happens to be 1 minus x squared. So it's not a difficult substitution. In fact, it's a pretty straightforward one. Everything we needed for the du package was there. But what would happen if that failed? This worked nicely because we had that extra x marked out in front of the square root, which was necessary for building the du package. But what if that x wasn't there, like it is in the second one? Let's try to integrate this using substitution and see what happens. Warning, it's going to crash and burn, but that was by design. All right, Now that we've cleaned that mess up and documented the answer to the first one, let's try the second one. And your motivation might be to use the exact same substitution. And there's nothing wrong with trying that. As I've mentioned in previous videos, you cannot be afraid to try and fail. That's part of the learning process. If we let u equal the radicand, the 1 minus x squared, then du is still going to be negative 2x dx. But there are no x's with which to create the du package. So is there a way around this? Well, sort of. You can still balance out the negative 2. That's not a problem. We could sneak an x in here, but we would have to balance it inside the radical with the 1 over, inside the integral with the 1 over x. But then when we make our substitutions, we'll have a stray x in there. And then we could solve this for x. If we solved it for x, we would get x equals the square root of 1 minus u. But I don't know if I want to sneak that into the radical under that fraction when I'm trying to get this thing ready to integrate. That's just going to mess it up some more. So yeah, this choice of substitution, although at some point it would make the problem difficult, if not impossible to do, is the natural choice. However, there's another substitution we can make. We can make what's called a trigonometric substitution. A trigonometric substitution basically means that we have an algebraic integral that we're going to turn into a trigonometric integral. Now, why on earth would we do that? Well, I'll leave you with a little teaser. It'll take us to the next video. Notice the radicand, the part under the square root, is 1 minus x squared. If you think of that as, well, let's just put it this way. We have some trigonometric identities that contain an expression of this form, 1 minus something squared. In fact, there's two of them. One of them is 1 minus sine squared, we'll say theta, equal to cosine squared theta. Now, why would that be advantageous if there was a sine squared there instead of an x squared? Well, because 1 minus sine squared is cosine squared, so it collapses it from two terms to one term, and that, living under a square root, would simplify to just cosine. So let's take this in the next video.